back in the last unit, structure and bonding, we did about different ions and how they are actually formed. In this unit, what we're going to be doing is applying a new context to that. So, what is an ion? Last lesson we just defined it as an ion being is formed when atoms gain or loses electrons to achieve full outer shells. And you can give a special name to these two different ions. There is a cation, which you get when a metal loses an electron, or you can get what we call an anion for when a non-metal gains an electron. Silly way to remember that. Have I animated it? No, I have not. Silly way to remember that is the onion makes you cry. So if that is an onion, but it's actually an anion. And onions make you cry, anions have a negative charge, okay? So what this should look like depends on if you're dealing with a metal or a non-metal. In this example here, I have got the metal atom sodium. And sodium is in the alkali metals. It's on the left-hand side of the periodic table. And they all have one electron on their outer shells. Because they have one electron on the outer shells, they're extremely reactive because they want to lose an electron to achieve that full outer shell. So feel free at this point, if you like, to have a quick sketch of the sodium atom. You should be able to do this. This was a skill from structure and bonding. Have a sketch of it and predict what its ion would be. So what we are expecting to see here is this electron being lost. And that is indeed what we get. So the outer shell goes, and now this one would be classed as an outer shell. We've got 2 electrons here, and then 8 on the new outer shell. And as we saw in the previous unit, we put square brackets around the outside just to show that we have got an ion now, because the ions will have a different charge. Up here on the top right, I've got my little cation then with its little positive charge. Ha 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 ha. Just to remind you that that is the key language that we should be using right now. Okay, predict what you think it will do for a non-metal. Metal atoms will lose electrons to form positive cations. What will non-metals do? The non-metals gain electrons to form negative anions. So in this example here, we have got a chlorine atom. Chlorine being a halogen, it is in group 7. Because it's in group 7, there are 7 electrons on the outer shell. So the chlorine has got a little cheeky space there where another electron could squeeze on to achieve the full outer shells. So when it does that, this outer shell gains one more electron and it ends up looking a little bit like this. Okay, 2 electrons, then 8, and then another 8 on the one after that, with a leftover positive charge. Because it has gained something negative, it becomes negative. For example, if I give Finn a detention, he's going to be feeling negative. So, chloride is an anion. It has got a negative charge. Here's a little cheeky onion again with its little minus charge. And a thing to remember that we should know from structure and bonding is with non-metals, they change the ending of their name. So this has now become chloride and an ion rather than an atom. So here we've got a chlorine atom, here we've got a chloride ion. This is basic stuff from earlier on in year 10. Okay, next section. Where do these electrons come from or go to? So we've said that the different atoms are going to gain or lose electrons to become ions, but where do these electrons actually come from, or do they actually go to? Now, once again, in structure and bonding, we did talk about them forming an ionic bond. For example, lithium, and let's go something like fluorine. Lithium loses one electron and keeps a positive charge, gets a positive charge. Fluorine gains the electron from the lithium to become a fluoride ion with a minus charge. Since those two have opposite charges, they have what we call an electrostatic attraction, i.e. they're opposite charges, so they kind of stick together in what we call an ionic bond. Now, what can happen in some cases is if there are different elements present, a little fight can almost break out between the elements, the atoms, the compounds, in order to kind of discover and figure out who gets to take the electrons. And this links back to a really nice idea from back in year 9 called displacement. Question: what is displacement? Displacement. Back in year 9 we talked about displacement in a number of different ways. Here is just one example of it. So here we have got iron and oxygen. That is forming the compound iron oxide. Iron is a metal, oxygen is a non-metal, metal plus a non-metal equals ionic. That does look like it's got a does not equal. That's supposed to be an equals ionic. However, if a different metal comes along, for example, magnesium is way more reactive. So what it's going to do, as you just saw in that little silly example there, is the magnesium is going to come along, more reactive, and go, oh, I'm going to have that oxygen for myself. And the ion is forced off to go somewhere else. Okay, so displacement can be described in a whole different ways. And actually you can see in Q16 on the board next to the fume cupboard, on the left hand side of the room as you're facing the whiteboard right now, that are some posters about this. These were made by the top set year 9 boys about 2 years ago, so the year 11s as they are now. And they are different models for describing displacement to help people try to understand it. One of the models that is up on that board is the bad boyfriend analogy. So here we've got little Miss Iron and Mr. Sulfate. Ah, look at them holding hands. Aren't they so cute? Ooh. Here comes Miss Zinc. Look at her with her purple t-shirt and yellow hair. Wow, isn't she pretty? She's got a good tan as well. They both do. Uh-oh. Uh-oh. Mr. Sulfate is a bad boyfriend. Mr. Sulfate is going to run away with Miss Zinc. Oh, look, they're in love. Isn't that lovely? Oh, Miss Zinc, Mr. Sulfate, but poor little Iron is left all there by herself. Ah, say it together. Ah. Okay, again, just a silly example of explaining displacement reactions. And from this, we can actually put together a word equation from this. So iron sulfate plus zinc is going to make zinc sulfate and iron. Here we can see an ionic compound having the metal part of it, the iron, displaced by the other, more reactive metal part. So the zinc steals the sulfate to itself to make a new compound, and we're left, therefore, with a metal element. Apologies for the awful handwriting there. It's not easy to do with a mouse. Okay, so that is a displacement reaction. That is the definition for displacement reaction. So, the reactivity series. Why are we talking about the reactivity series? Well, the reactivity series will affect this idea of displacement. So when a more reactive element removes something from a less reactive element, we do need to know the reactivity series. The reactivity series goes, please stop calling me a cute zebra. I like hugging and cuddling small goats. Please stop calling me a cute zebra. I like hugging and cuddling small goats. Silly way to remember it. There are obviously other ways to remember it. Some of them rude, some of them not rude. You're very welcome to come up with your own way of remembering it in your own time. The elements that this matches to. Now this in theory is the reactivity series of metals. But we have included some non-metals in there just to make it more useful for a few different things. We do need this in particular when we're talking about electrolysis. So let's have a look. The P, potassium, S for sodium, C for calcium, M for magnesium, A for aluminium. This C here is not a metal. This C here is carbon. So that is a non-metal. Z for zinc, I for iron, L for lead, H for hydrogen, which again it's in bold there because it is a non-metal. This C is for copper, and this S is for silver, and this G is for gold. So that is the reactivity series of the metals. Now later on this unit we will be using this a lot to help us predict the products of electrolysis. Back in year 9 you potentially used it to figure out how certain elements can be extracted from their ores. For example, anything less reactive than carbon can be extracted via a displacement reaction with carbon. However, things like silver and gold are so unreactive, they occur native, is the la-di-da way of putting that. That means that they're just naturally in the soil anyway. Anything more reactive than carbon must be extracted using electrolysis, which again, this is what this unit is going to be about, electrolysis. We'll deal with that properly in due course. You do need to remember the reactivity series. You do need to be very comfortable using it because you may be given a scenario where you're expected to predict the products that are made in a chemical reaction. For example, and it's a silly example because it's me. So this artwork was done by an artist online. I've got to get credit for using their work. I've got to give them credit for their work. It's absolutely gorgeous. They've made different characters for all the different elements and made them into kind of superhero characters, which again, love it. So here on the left, we have got silver. Silver, the best conductor of electricity of all the metals. So why don't we use it more often? Because it's not that easily available. Potassium on the right hand side, purple potassium, my favourite element. It is very reactive and it burns with a lilac flame, lilac being a shade of purple. So everyone, what I'd like you to do is to predict which would, they had, let's say, oxygen atom, which one would be able to steal the oxygen from the other. Hopefully you have all gone for this one. Potassium is the top of the reactivity series. There are obviously more reactive metals than potassium, for example, rubidium and cesium. However, they are not covered in their reactivity series because they're very rarely talked about at this level. Potassium is way more reactive. Anything silver had, whether it be silver oxide, silver chloride, silver carbonate, silver nitrate, the potassium would be able to steal the non-metal part of whatever it was bonded to. So it would form potassium chloride, potassium nitrate, potassium oxide, whatever it may be. Okay, same again. Let's have a look at this example. We have iron rust by itself, which is why a lot of elements are added to it to make steel. Magnesium there. The only way to put out a magnesium fire is with sand. Have a check of your reactivity series. Which one would win? If they were fighting over, let's go bromide, iron bromide, magnesium bromide, who would win? Awesome. I like to think we have all gone for magnesium. Please stop calling me the me bit. It stands for magnesium. Magnesium is more reactive than iron. So if there was a compound of iron bromide, the magnesium would take the bromide all by itself and the poor little iron would be left on its Todd in its elemental form. Okay, so that was just a very quick way of just checking your understanding of the reactivity series. So, in this next bit, what we have got here are some examples of what we call displacement reactions. What I'd like you to do is use the reactivity series and what we've just discussed to predict the properties that will be made in these reactions. Okay, so the answers for this section then. What we are looking for is if the metal part is more reactive. So which metal is more reactive out of copper and iron? Iron is more reactive, so the iron is going to be able to steal the sulfate to itself and the copper is going to be left over. So you're going to get iron sulfate plus copper. In this example here, the two metals present are copper and copper. Copper and copper are the same element, so there is no reactivity difference there. Therefore, there is going to be no reaction. Number 3, metal that we've got silver and we've got copper. Which one is most reactive? Copper, but only just. So copper is one place above silver. So the copper is going to be able to steal the nitrate for itself to form copper nitrate and silver. And last one at the bottom here, iron versus silver. Iron's going to be more reactive. Iron's going to steal the nitrate to itself. So you're getting iron nitrate and silver. The extension task was to write these reactions using chemical symbols. So let's have a go at doing that. Right then, here we are. So this section here uses my Remarkable, that's the name of the tablet thing that I'm always carrying around, and it's just a bit easier for me to write on it. So if we are looking at the symbols of these, we do actually first off need to know what these extra sort of weird and wonderful bits are. Sulfate is SO4. Nitrate is NO3. If you have not done this task and you needed those two bits of information to do it, you are very welcome to request that the teacher pauses the video, or if you're watching this yourself, you can pause the video yourself and attempt to do the rest of this task. I'm going to carry on. Copper symbol is Cu. Sulfate symbol is SO4. Back in structure and bonding, we talked about in ionic compounds, whenever you write a formula for ionic compounds, you have got to check if the charges balance. Copper is a 2+ ion, sulfate is 2-. They cancel out, so that is absolutely fine as an ionic compound there. So copper sulfate plus iron. Iron is capital F, little e, and it's going to make iron sulfate. Now, iron can exist as +2 or +3. You don't need to worry about too much in this example. I'm just going to ignore the +3 bit. I'm going to treat it as if it were +2 because that just makes it a straight swap SO4, because the Fe here would be +2. This one is the -2, that just cancels out, so that's absolutely fine. Plus the elemental copper. For number 2, there's no reason to do number 2 because there was no reaction. For number 3, we've got silver nitrate. Silver is Ag. Nitrate is NO3. Silver has a +1 charge. Nitrate has an NO- has a 1- charge. So again, in terms of ionic compounds, that cancels out. These charges that I'm mentioning, they were given to you back in structure and bonding in a table of different bits and bobs with all sorts of different charges. You do not necessarily have to memorize them all, but it is faster if you do get a good understanding of these. So silver with a nitrate group plus your copper, capital C, lowercase u, is going to be swapped over. Copper we've already said was we said it was +2 last time, didn't we? Oh, that's a bit cheeky then. Hello, sweetie pie. And by sweetie pie, oops. Hi, sweetie. Bear with me. Are you coming to say hello? Oh, she's going now. It looks like I've said sweetie pie to no one. That was my daughter. Sorry, I didn't get the screen switched. She came in and said hello. Here's Mr. Bateson.
It was me. I'm sweetie pie. It's me. That's me.
Mr. Bateson has been making videos as well, and his has actually got a theme tune. We're in a bit of a competition at the minute. So feel free when you get home to like this video just to screw over Mr. Bateson. Anyway, lesson. What are we supposed to be doing? 15 minutes left. Right. Where was I? Remarkable. Screen. There we go. Cool. Just checking that works. So, silver nitrate. Yes. So, silver nitrate we said was -1. So, -1 here for that entire sort of block there. Copper we said before was -2. Now, copper again can be -2 or +1 or +2. You don't need to know the difference at this point, but okay, let's just imagine if it was +2. Let's put that in brackets. So that entire thing has an overall charge of -1. That has an overall charge of +2. So to get those two to balance, we need 2 lots of this thing, which we represent just by putting a 2 there. Now, silver is just Ag. That section there is a higher level stuff. If you struggled with that, that is fine. That is normal. We'll talk about that properly another time. And then question 4, here we go. Silver nitrate, AgNO3, exactly like we had for question 3, plus iron, elemental form, capital F, little e, is going to make iron nitrate, Fe. Nitrate is your NO3. Let's treat this as if it was the 2 plus iron, and then we just do the same again. Square brackets around that, and because each one of those is a lot of -1, and plus the silver. So that is why this was an extension task. It's a little bit trickier. Okie dokie, let's head back to the lesson PowerPoint and see what else we've got to be talking about now. Now, I will be coming back to these reactions to add something called a half equation. We'll come on to that in a few minutes. Right, these two words are extremely important for this topic. Oxidation and reduction are very, very important. You might have heard of these before, especially back in year 9 when you did a unit on metals. And you may have defined oxidation as the gain of oxygen, which makes sense. If a chemical is oxidized, that means that oxygen has been given to it. Oxidation and reduction are the opposite of each other. So if something is oxidized, it has gained oxygen. If it is reduced, you've reduced the amount of oxygen something has. That makes sense just from a sort of linguistic, logical point of view. However, when we come to electrolysis, we have to define oxidation and reduction in terms of the number of electrons. And to help you remember this, a little technique that science teachers have been using for absolutely donkey's years is oil rig. You'll see it in a lot of revision guides, you'll see it on a lot of revision websites, oil rig. That is just... do they call it an acronym? Something like that. An English teacher will know. But oil rig. Oxidation is loss. Reduction is gain. So oxidation is loss of electrons. Important to point that out because we've just said that it's gain of oxygen, but it's loss of electrons. And reduction is therefore the opposite. Reduction is gain. And again, in the context of electrons. Okay, so if something has gained or lost electrons, we can say it has been oxidized or reduced. What we're going to do is I'm going to show you something called a half equation, and we're going to try to apply that language to those examples. So I'm actually going to go back. Too many windows open. I'm actually going back to that Sorry, just had to double check there you were seeing what I was hoping you were seeing. So in these reactions here, one species will be by species I just mean one chemical. One chemical will be oxidized, one will be reduced. So what we do is we can break these full equations into what we call half equations. So with this copper sulfate, the copper I said before was there as 2 plus, and the sulfate was there as 2 minus. So the copper has started in an ionic form. This here is altogether, this is called just a chemical equation. I'm going to break it down into a half equation. In half equations, you just see one lot of ions being converted to one lot of atoms, or vice versa. So here, the half equation, the ion, the copper is present in its ionic form. It's there as Cu2+. On the right-hand side of the equation, it is present here as just its elemental form, Cu. Now, when we're writing half equations, we have got to check that there are the same number of chemicals and charges on each side. On the left-hand side here, there is just one block of copper. On the right-hand side, there is one block of copper. On the left-hand side, the overall charge is +2. On the right-hand side, there are no charges at all. Sorry for the screaming in the background, that's my daughter shouting about lunch being made. So what we're going to do is we have to get the charge same on each side, and the only thing that we can do is give one side of the equation or the other side of the equation electrons. So electrons always have a negative charge, and we represent them in an equation as E-. So I'm going to put the electron here. So now this left-hand side, I have got 2 lots of positive and 1 lot of negative. If I added that together, I've got 2 lots of positive minus 1, that is still +1. So what I need to do is I need to give it 2 lots of electrons. And that is a half equation, a balanced half equation in fact, because I have balanced my number of electrons. In this example, it is it oxidation or reduction? Oxidation is loss of electrons, reduction is gain. The copper ion here has been given electrons, so this has been, well, this is the reduction reaction because it has gained electrons. There we go. Gained electrons, it is a reduction reaction. The sulfate, the SO4, hasn't actually changed. It's just switched from one place to another and not changed its charge at all. So actually, I'm going to ignore that. At higher levels, we call that a spectator ion. And we do not include spectator ions in half equations or in ionic equations. Now we need to do the half equation for iron. So iron on the left-hand side starts as its elemental form, so capital F, lowercase e. On the right-hand side of the equation, up here, we had it as a 2+ ion, so Fe 2+ ion. Now that's an ion of iron. I hope that makes sense. Okay, I've got one block of iron on the left-hand side. I've got one block of iron on the right-hand side. That is balanced. In terms of the charges, on the left-hand side, I have 0 charge. On the right-hand side, I have +2 charge. So I need to cancel that out. And I'm going to do exactly the same as I did with the copper. I'm just going to give the side that originally had the positive charge 2 electrons to cancel it out. So each side here has got a 0 charge overall. This little bit of iron has lost an electron, well, lost 2 electrons. It's lost electrons, so this is the oxidation reaction. Okay, so there's oxidation and reduction happening in this displacement reaction. And because we have oxidation and reduction happening, we simplify these those two words and we put them all together and we call this a redox reaction, which was the title of our lesson. So the idea of electrons and displacement coming together gives us the idea of a complex relationship between the two called a redox reaction, in which some of the chemicals are reduced, i.e. they gain their electrons, some of the chemicals lose their electrons and therefore are oxidized. The rest of the PowerPoint here, there are some other examples of half equations for you to have a go at now, because your homework is going to be to finish this sheet on half equations and then to check off your answers, mark it, and I'll send that all information to Edmodo for you. Okay, going back to finishing off these ones in terms of their half equations. Very, very similar idea. So I'm going to start with the silver. The silver is here in its ionic form of a +1, and it changes on the right hand side to an elemental form of just Ag. There's a positive charge on the left hand side, so I'm going to cancel that out with a negative charge there. For the nitrate bit, the charge has not changed, therefore it is a spectator. I'm not going to bother talking about the nitrate bit because its charge stays as 1-. The copper, however, goes from being an elemental form with no charge to an ionic form with a charge of 2+. There's no charges on the left-hand side, but there is a charge on the right-hand side. So what I need to do is to cancel that charge out. Here we go. Sorted. Okay, those are the half equations there. This one has gained an electron, so is reduction or reduced. This one on the right hand, this copper one has lost electrons, so that has been oxidized. Silver, ionic form, Ag+, sorry. Here on the right hand side we've got just the elemental Ag plus an electron, job done. Ignore the nitrate, iron has gone from its elemental form to its ionic form, 2+, cancel out that by giving it 2 lots of minus. There we go. Very, very quick whistle stop of those compounds. Okay, please do make sure you have a go at the worksheet, whether it be a hard copy or a digital copy. In fact, I might even put it on Edmodo as a quiz. Make sure that you have understood it all. So that is it for today, ladies, gents, girls, boys and others, however you choose to identify. I hope that has been helpful to you. Please do head on to Edmodo and on the YouTube channel. Oopsie daisy. There we are. Check out Edmodo, check out the YouTube channel. All sorts of resources are going to be sent to you. The next lesson I have with 10 Set 2, the original class that this video was attended for, isn't until next week anyway. If the school closes officially, like the government closes us down, then what we will do is set you a different project to be getting on with rather than doing live streams like this. And then we will continue electrolysis when we all return to school at whatever time that might be. Okay, hopefully that's been useful. Message me if you need any extra help. Edmodo is the best way to get hold of me. However, my school email address is obviously active at the minute as well. So do whatever you need to do. That is it for now, ladies and gents, girls, boys and others. Be gone, minions of science. Bye.